announcements today. So I think everyone was a little bit tired yesterday, so I cut off questions at a certain point. Are there any questions? Well, first of all, are there any urgent questions from yesterday's lecture? And then are there any less than urgent questions? All right, so if you remember the questions during the lecture, you can ask them then. So we've been looking at how to compute one-loop amplitudes. And we looked yesterday at the sets of integrals and how to reduce them to a basis or a set of master integrals. And then we saw how to use that master equation to derive some useful identities, and in particular for the coefficient of a box, then we found the formula where we sum over the two solutions to the quadruple cut equations. We summed over species, which in our investigations here, we're just going to focus on gluons, but we also have to sum over helicities. And then we have 4 amplitudes which we then need to evaluate around the cut loop. And this formula is originally due to Brito, Cacciazzo, and Feng. Let's see if there's a yellow chalk here. Really should have more brighter colors. Anyway. So we want to do an example. So let's look at computing the coefficient of a one-mass box integral. So K2, 3, 4, 5 in the 5-point amplitude 1 minus, so this is a one-loop amplitude. We're going to look at the leading color contribution, because as I explained yesterday at one loop, the sub-leading color contributions are just sums of leading color contributions, so you don't need to compute them independently. And we're going to look at the quadruple cut. So let me draw it here large so we can decorate it. So let's label things. So this is going to be leg 1, negative helicity, leg 2, 3 plus, 4 plus, 5 plus, and let's also label the internal momenta, which of course here are going to be cut and on shell. I'll try to label them with the index of the leg that they're flowing into. So this would be L5, and this will be L1, and this one will be L3. So the first thing we have to do is assign helicity labels here. And here we have a 4-point amplitude, and we know that if you have too many or too few negative helicities, then it's going to vanish. So in fact, the only assignment that's possible here is plus plus. If I chose, for example, minus minus, it would be an all minus amplitude. It would vanish. If I chose plus and minus, it would be a single plus amplitude, and that also vanishes. Now again, as we're crossing the cut, the convention is, and we're going to keep track of that when we write down the spinor products, is that the sign of the momentum and hence the sign of the helicity is flipped. We want to keep that convention because we're going to use 3 and 4 point amplitudes that we've previously computed. Remember, this amplitude we actually computed explicitly on Tuesday. So here we're going to have a minus, and here likewise we're going to have a minus. But that doesn't tell us right away what we're going to have here. So let me use sigma 2 plus or minus, and then of course this should be minus sigma 2, and similarly here I'll label this with sigma 1, again plus or minus 1, and then therefore minus sigma 1. So now we have to look at all the helicity configurations. I need a larger piece of chalk here. Let's see if this one is manageable. Oh, it's actually weaker. So let's write them down. So let's start with a simple one. Let's suppose we choose them both to be plus and plus. Actually, this is backwards. Sorry, I'm going to choose them to be minus and minus. So then this is going to be plus, this is going to be plus, and that's going to be a plus. So we have an all plus 3 point amplitude. And that's going to give us an A3 plus plus plus, which is equal to 0. So we don't need to worry about that contribution. And I hope I have the signs. I have the signs backwards here. We'll find out in a minute. So if we choose the sigma 2 to be plus, this is minus plus plus. And sigma 1, this is then plus plus, and again a minus. So that both of these could be non-vanishing, but there's an issue, right? Because in order to get a plus plus minus 3 point amplitude, we had to take all the angle spinors to vanish. And the interpretation of that is that the angle spinors are collinear. They're proportional. So this would require, among other things, require that lambda 3 be proportional to the spinor, the angle spinor that's attached to L4. But here it's the same thing. Plus plus minus would then require that that same angle spinor be proportional to the spinor for the external momenta 4. So that's saying that the spinors for 3 and 4 would have to be collinear for this to give a contribution. But that's not generically true. We're computing this thing for generic external momentum. So in general, if we just choose some arbitrary external momentum, this statement is not going to be true. And what that means is that this contribution is also going to give 0. And that's a general kind of feature. If you're doing a cut and you're trying to sew 2 3 point amplitudes, then 2 adjacent amplitudes of the same chirality will give you 0 for generic momentum. And the same argument holds true for plus minus. That's also going to give you adjacent similar chirality on the right-hand side. So that's also going to give us 0. So that leaves us with just one contribution, which is plus plus. And so this thing, you'll be relieved to know, does give you a non-vanishing contribution. So in order to compute it, then we can find the, so here, let me just say, we're going to have a, plus plus minus, and that's going to tell us that this part of the equation is going to be true. So that suggests that we should build our solution by maybe focusing on L4, and so L4 is going to be proportional to some angle 3 spinner, and on the other hand, on the other side, we're going to have a minus minus plus, so it's the bracket spinners that are going to be proportional, so we should start by building it from an angle 3 and a bracket 4 spinner. Let me assume everyone has recorded that. So let's start by thinking about well, put in a 2 here, it doesn't really matter. To start with parametrizing the cut momentum, we know, of course, that one of the cut conditions we have is L4 equals 0, so this satisfies that. And then if we look at L3, then we find that that's, of course, L4 plus K3 squared, and so that also is automatically going to be 0. And L5 squared is going to be L4 minus K4 squared, and again, that's automatically going to be satisfied. That's the same pattern we saw yesterday, that choosing this bispinner form with spinners associated with the external legs gives us 3 equations. And there's one more equation that we need to impose, which is L1 squared equals 0. And that thing will give us the value of C. And we can just write it out. So we're going to have L4 mu, the cut momentum on the upper part. We can write as the ratio of 2 angle products, 4, 5, and 3, 5, with an extra factor of 2, multiplied by this vector that we started out with. So again, we can do a quick sanity check. There's no spinner weight with respect to 5. There's no spinner weight with respect to 3 because they cancel between numerator and denominator. And the spinner weight for legs 4 will be opposite, assuming that we go back to real momentum. And so again, it'll have no spinner weight with respect to leg 4. And we can now write down all the spinners that we have. So again, all of L1, L3, L4, and L5 are on shells, so we can write them as spinners. So we can just talk about the relevant spinners. And we have, just by doing momentum sums or differences, and then doing the appropriate combining and using the Schouten or other identities, we can come up with these forms. And I'll just write down the results. It's good to work this out for yourself. So there's an ambiguity here in the overall normalization and certainly in the phase between the angle and the bracket spinner, because I could multiply this by something and divide this by the same something, but at the end of the day, it's not going to affect the result. And if you want, you can go back over this calculation later and check that explicitly. So in contrast to the vectors, the spinners, of course, do carry a spinner weight. And here, the normalizations have been chosen so that, for example, spinner 1 carries the same weight as 5, but the conjugate spinner will carry the opposite weight. So again, the vector will be free of a spinner weight. So not everything is boring for the angle spinners. Let me write down L4 here. And all we have left to do now is just to substitute in the explicit, the relevant legs into this formula here, and then substitute in those formulas, and then do a little bit of algebra to simplify things. So actually, let me come back to this exercise at the end. So our quadruple cut formula says that our coefficient is going to be equal to 1/2 a tree. So we have 1 4-point tree, 1 minus, 2 minus. Oops, sorry. It's not the right orientation here. I'm going to try to write it in a form that goes around the cut loop. So that will start with minus L1 plus, 1 minus, 2 minus, and then L3 plus. Of course, cyclic invariance of this thing would allow me to write it in the other form, but I'm just going to try to write it in a form where you can trace the loop momentum around the circle. So a tree, and this is a 3-point, everything else is a 3-point amplitude. And again, you can see that the sign of the momentum is flipping as we go across each of the cuts. So we know the expressions for all of these because those we derived on Monday, and this one we wrote down, we actually computed on Tuesday. And anyway, it's the n equals 4 case of the Park-Taylor formula if you don't want, if you were asleep during the actual computation. So we just write out those expressions, and again, we'll extract out the minus signs keeping track of the factors of I that are associated with it. So here we have, for example, the angle product of L3 with minus L1. And here we have, whoops, let me write it a little bit more neatly. 1. And I think I can squeeze in one more here. 3L4 cubed. So again, the plus minus is with bracket products. I may not have kept a precise track of the overall factors of I, and therefore there might be a sign that I'm leaving loose here. I leave that as a homework exercise for you to fix up. Board is a little bit slippery at the right end. Four L5, and minus L5, 5 cubed. And again, the opposite chiralities have to alternate so as not to impose constraints on the external momenta or the external spinors. Okay, so the next step is we just take our expressions for the spinors, we plug them in, we remove all the various factors of I that are associated with the minus signs, and when we do that, we get something that is starting to show some of the features that we expect. So there are some spinor products that we expect to see in the denominator, like 2, 3, and 5, 1. Those are nearest neighbor spinor products. The other ones kind of look weird because they don't show up at tree level, and it's not exactly clear what's going on at loop level, but somehow they may not look exactly right. Let's see here, we have 3, 5. But they also show up sometimes in the numerator. And we have 4, 3 squared. I think I should stop at that point on the board. And we have 5, 4 cubed, 3, 5. 4, 5 squared, 3, 4, and then there's a minus 1, 4, 5 cubed times. So here we don't actually have to use momentum conservation. We just need to cancel things across the different factors. So sometimes you'll see that things cancel within the same factor, sometimes not. And what this turns out to be is something that you recognize already. 2, 3, 3, 4, 4, 5, 5, 1 times S34 times S4, 5. And this thing, I think everyone recognizes by now. What is it? Come on, are you still all asleep? You should be woken up after Alfredo's lecture in the morning. I'm sorry? Yes, it's the Park-Taylor amplitude. It's the tree-level Park-Taylor amplitude. And so this thing is actually over 2 times the tree level amplitude for the same helicity configuration. Now, the other thing that you may not know, and you will learn it probably in about half an hour or so, actually possibly at the end of the closer to the end of the lecture. But this is actually the same as the denominator of the box integral. So this actually cancels the dimensionful denominator of the corresponding box integral. And so in a sense, we're left just with the discontinuity containing functions after you multiply this. So there are a few comments that are worth making. So this is, of course, a contribution in QCD. Just one second, let me finish this. And there are going to be other contributions to the same amplitude from triangles, from rational contributions. But it turns out that this is the same coefficient in n equals 4 SUSY, so in n equals 4 supersymmetric Yang-Mills. And there are actually no other contributions. There are no triangle or rational contributions. And in fact, this box and its partner boxes give the complete answer. And moreover, thanks to things called supersymmetric word identities, I don't know if Henrik discussed them at all or no. So that's not something you'll see in any of the lectures this week. But it turns out that in the n equals 4 case, you can get all the other contributions just from word identities. So this one computation, you've actually computed a complete 5-point amplitude at one loop in the n equals 4 supersymmetric Yang-Mills theory. And that's something which would have been, when it was first done, I guess kind of around the time many of you were being born or even before, then it was a very challenging calculation, but it's now something you can literally do on the back of an envelope. So that's how technology progresses. So there was a question. And please use the microphone. So let's see if any of these is charged. Yes, this one seems to be.
There should be one other momenta, right?
There should be one other
momenta, one of the solution for L square.
Yes, and actually that's a good point. So that's an exercise. So I'm not going to tell you. Exercise. What happened to the other solution for L4? So thank you for reminding me. Do we have a discussion session this afternoon, or okay? If I'm there, I can encourage someone to tell me the answer. Yes.
Hi again. Was it accident that we have like exactly the 5-point amplitude for the in the coefficient?
So you're saying, is it an accident that the tree amplitude shows up here?
Yeah.
So first of all, this isn't a general feature. If you compute some arbitrary, more complicated amplitude, you're going to find a more complicated answer. But in a sense, no, it's not an accident. And you can understand that within the context of the n equals 4 theory, that there's the structure of infrared divergences, which we're not really going to have time to discuss, is such that they have to be proportional to the tree amplitude. And because here the infrared divergence is essentially carrying along the rest of the box in a very constrained way, then there wasn't much choice actually for it to end up this way. But until you did the computation and until you actually understood some things about n equals 4 Yang-Mills, then you could probably have conjured up some way of satisfying all those constraints, but in fact, this is the most natural way to satisfy it. It may be the only way. I've never really thought through the problem in that context. But so no, it's not an accident. Okay. Yes. Yes. Yeah.
Soaks up all the poles as well.
Yeah. Okay. So we're not going to have time to study formalism for doing calculations at higher loops in as much detail. In fact, some of that is still, I would say, at least to my taste, a work in progress. So there are still good thesis problems for people who are interested in somewhat more formal and technology development ideas. But we are going to look at kind of how to get the analog of that master equation that we wrote down at one loop, and in particular, the question of how to derive which set of Feynman integrals arise, and also not beyond one loop, but how to go about calculating the actual Feynman integrals. So the next simplest thing beyond one loop is, of course, two loops. And we're going to find three new features. That are pretty much representative of what happens at two loops and beyond. And it's going to be convenient to refer to the vacuum integral in order to build and classify and label two-loop integrals. So here, of course, we have three different loop momenta, which I will label this way. And of course, they satisfy a relation. I think I wanted to actually label it the other way, but anyway, L1 plus L2 plus L3 is equal to 0. And we can get general two-loop integrals by attaching external lines to this vacuum diagram in various ways. And if we call Ni the number of external legs attached to Li, then, of course, without any loss of generality because of the symmetry, we can take N1 bigger than or equal to N2, which in turn is bigger than or equal to N3. And in addition, if we're counting massless legs, we could have either 0, 1, or 2 attached to either or both of the vertices. And the structure for attaching more than two massless lines doesn't really change the analytic structure because it's basically just having a massive leg attached there. Having a massless or massive leg can change the analytic structure. So in the case that N3 is equal to 0, then we have a planar integral because it can be drawn on a sheet of paper without crossing lines. If n3 is non-zero, then we have a non-planar integral. And that's actually the first new feature that arises at 2 loops. So that's the first new feature is the emergence of non-planar integrals. So let's look at a 2-point integral. I'll draw it this way. So again, the two lines close together, they denote a massive momentum. So let me label it with capital K. And again, L1 here flowing this way, L2 flowing this way. And here, of course, has to be minus K directed outwards. So let's count the number of independent invariants involving the loop momentum. So first of all, of course, we have L1 squared. We can have L2 squared, and we can have the dot product of the 2 loop momentum. But there's more. So these are the ones that are quadratic. We also have a pair that are linear in the loop momentum. And we can have L1 dot K and L2 dot K. And we can throw, if one wants, into the mix there's only really one invariant of external momenta, which is K squared. But we only have 3 propagators, and so even with the help of the external invariant, we cannot write all of the invariants involving the loop momentum as differences of propagators up to some external invariant. So that was a very critical aspect of reducing things at 1 loop. So the leftover scalar products, which here we can take to be these two, that's the other new feature that we see at higher loops. Now, the fact that we have these leftover, what are called irreducible scalar products, or ISPs. So at least in English-speaking countries, ISPs would, to the general public, mean something completely different. I don't know what the corresponding term would be in Portuguese, but it's an internet service provider. So, but I guess for Portuguese speakers, there's no confusion here. So you can still, not all of the products are going to be ISPs. There are going to be some that can be written in terms of propagator denominators, and those are, of course, called reducible scalar products, or RSPs. And that means that the same partial fractioning ideas can be run, the same Gram kind of driven reductions can be run. It's just they're not the complete set of linear identities that you can find. I'm not going to discuss that reduction in detail. We will come back. Actually, we will go on rather than coming back. I think, yeah, we'll go on to see what we can do to simplify the structures of integrals with ISPs. But generally speaking, we will need to consider all integrals that have up to 4L propagators, and integrals that have more than 4L propagators generically will be reducible either up to terms of order epsilon or with no terms of order epsilon to integrals that have just 4L propagators. This is not, I don't think this is a statement which has really been proven beyond 2 loops, but it's the expectation that I would have. So let's suppose we have some set of ISPs, which I'll label W. So, and the number of them depends on the number of loops. It depends on the number of external legs. And here there were 2, but in general, there could be more. In the other kind of canonical, let's say, simplest integral to think about for a lot of purposes, which is a 4-point integral. This is called the double box because there are 2 boxes there. Then again, there are going to be 2 ISPs, but there can be more or less depending on the integral involved. So the worry we have, or let's say is that the opportunity is that if you have some integral, and again the bracket notation means that we're putting this into the numerator, that if we have some string of ISPs with various exponents, and the exponents here are understood to be integers, that these are all independent. And that we would have to evaluate them independently, and that they all have to be inside the basis. And of course that, the kind of line 1 worry is that this is actually an infinite set of integrals because those exponents can be anything. Now, of course, in any specific theory like Yang-Mills or gravity, then there's going to be some bound, but that bound is large, and so it's a large set of candidate master integrals. So I don't know if it's the sort of thing that would give you nightmares at night if you were thinking about it. I would suggest if that were true, you're probably thinking a little bit too intensely about physics, and you should relax before going to bed. But in any event, this is way too pessimistic, and in fact, there are a lot of relations between these integrals, and that's what we're going to spend probably really the balance of today's lecture on understanding. And the key to finding relations is something called integration by parts. Which is also more usually referred to by the acronym IBP. And the need and the opportunity of using them is the third feature that arises at higher loops. You can use them at 1 loop, and in fact, we'll kind of see an example of that. I don't think I'll get to it today. But it's not necessary, whereas at higher loops, it's really essential. And so if we consider some planar integral, but this applies equally well to non-planar integrals, it's just the example I'm going to give. So we have the measure, and I may not always be careful in writing out all the 2 pi's. So we have some integral with various legs attached to line L1 in the vacuum diagram, and so through N1, and then nothing attached in this example to the middle line, and then there's going to be some number of legs attached to the L2 line. So I'll refer to this object as just the denominator. So we want to try and find identities for this, and I have no idea what the intuition that led people to do this originally was, because it's not obvious that this is a good way to proceed, but we write down an equation that says that, and there's implicitly stuff which I'm not going to write out. So we're going to consider a total derivative. So we have some vector here. So if the integral were convergent, then this would be a total derivative, and it's very clearly 0. It's much more subtle for Feynman integrals, because if we weren't doing dimensional regularization, then generically we would need to do subtractions to make the integral convergent, and then this whole machinery would be much more complicated. But thanks to the dimensional regulator, we can treat all the integrals as being convergent, and then this is a manifestly true statement. We integrate over a total derivative, we get 0. So, and one example would be if we take, for example, V to be the loop momentum L1, then we can see that we're going to, as the derivative marches through, so again, it's an example of an identity which is true, but it's true non-trivially. It's not that the integrand is going to be 0. It's the integrand is going to be some mess in general, and each of those things will correspond to different Feynman integrals, and we're going to have a linear relation between them. And the basic idea is a kind of a brute force one, that we take all possible choices of V, so V here could be a loop momentum, it could be an external momentum, and then you take this whole huge set of equations and you solve them, and that will give you, eliminate all the extra linear relations, and will give you the set of basis or master integrals, in this case at 2 loops. So one of the things that you see that immediately is going to happen is that when you differentiate the denominator, then you're going to get higher powers of the denominator. So you're going to get integrals that have doubled, or in general, if you then have to differentiate them, you're going to get tripled propagators and so on and so forth. And at least in Yang-Mills and gravity theories, these integrals don't belong. They don't arise naturally. But it turns out that you can get enough identities to eliminate all of them. But again, there's a little bit of a parallel with gauge invariance, is that you have a lot of unwanted information in the intermediate stages, and so that makes, for a real-world problem, it makes for very large systems of equations, and it means that the codes that people have developed have to be very sophisticated in order to solve them in a simple or in a straightforward way. So the idea of IBP goes back to Chitirkin and Tkachov in a 1981 paper. And again, the intuition which led them to do this is very unclear to me, especially, and it was also unclear to a lot of other people, because it took 20 years to turn this into a much more general machinery that was suitable for general calculations. Nonetheless, I'm going to, I don't know if this is exactly the example from their paper, but I'm going to do a simple example. in order to, we can go here. In order to explain, or at least to show how this somewhat unobvious step can actually lead to useful relations. So again, we're going to consider a two-point function, but a different two-point function. So we're going to consider one which is sometimes called the kite, and which I sometimes call the lizard eye diagram. And again, we have, let's put K here, L1 and L2. And we can write it out. So again, there's the measure, L1 dL2. And then we just have 5 propagators. So L1 minus K squared, L1 plus L2 squared, L2 squared, and L2 plus K squared. So we're going to consider the related identity where we just stick in d by dl1 here. And here we're going to stick in L1 plus L2 mu. So we have a scalar. And there are various side calculations you can do. So L1 plus L2 mu times d by dl1 mu of L1 squared, for example, is equal to L1 plus L2 squared plus L1 squared minus L2 squared. Let me just write out one more of them. So you can see that even though we're differentiating here just with respect to one of the loops, both of the loop momentum get involved because of the L2 in the second term. And one other thing that is worth pointing out is that, of course, we also get terms where we differentiate L1 itself, and that just gives us the number of dimensions. So if we do the algebra, then I'm not actually going to write out the algebra, but I'm going to write it out in pictorial form. And so one term we get, in fact, is proportional to the original integral we started with. So we have an equation that's 0 because this total derivative is going to be 0. So we have this thing times d minus 4. So that's our original integral. And then we subtract something that has this form. So we've lost the central propagator. And this dot here is conventionally indicating a doubled propagator, so the corresponding denominator itself is raised to the second power, so it would be something like L minus K1, L minus K squared, the whole thing squared. And then we have essentially a reflection of the same object. So where the doubling is on the other leg. And so these integrals, because the central line has been canceled, they're actually just products of one-loop integrals, so they're elementary things which you could just calculate. And there's another pair which have this form here, where you've lost, again, one of the propagators, and here there's a doubling over here. And again, there's two things which are essentially the same, just up to some reflection. And here, the inner integral is again a bubble, so it's elementary. And then you get an outer bubble which has one propagator that has epsilon dependence in its exponent. The other one is just doubled. But again, the same straight direct Feynman parameterization that you can use to calculate the bubble, you can use to calculate these. So we can solve for this original integral, which can actually be done using Feynman parameterization and Gegenbauer polynomials and some other stuff, but is not as straightforward. We can solve for it in terms of what are truly elementary integrals. And in fact, when you do the exercise, so evaluate these integrals. So this technique, as I said, or this idea can be applied much more generally, but usually the integrals that appear here, when this is a more complicated integrals, they're not elementary. And also we have these doubled propagators that show up. And in general, in these systems, when you're doing this, you have actually a lot more integrals with doubled propagators than you have integrals of the sort that you're actually interested in. So it's a very non-trivial problem to solve these systems of equations in a way that is actually tractable. If you just, for kind of frontier problems, if you just wrote out all the equations and tried to hit it with solve in Mathematica, then I'm not sure it would finish before you retire. So that's not a good way of proceeding. And there are a variety of codes that people have come and gone over the years. The ones that I think are currently popular is something called FIRE, which comes from Alex Smirnov, Kira, which is Johann. I mean, there's other authors and people who are involved, but this is kind of the main author. Something called Kira, and then something which operates in a slightly different way, which is called light red, and that's due to Roman Lee. Let's see here. I don't know. I mean, Kira is independent. What exactly the exchange of information behind the new Iron Curtain is between Fire and Light Red, I'm not really sure. But and then people have their own private versions of all of these codes. Ah, okay. So. I think you could actually do without the symmetry relations. It's just the systems of equations would be larger. So from an efficiency point of view, it's important, but from an actually getting to an answer point of view, it's not essential. So I was planning to go through the Laporta algorithm in some detail, but I don't think there's actually going to be time for it, and there's other things which I think are more worth doing. So let me just sketch it out, just kind kind of to give you an idea of the complexity involved. So we can define this object V, which depends on the uppermost, which depends on the number of propagators, on the specific propagators that are chosen, on their exponents, and on the exponents of the ISPs. So this object is going to be the product over all the ISPs that we're considering, and NW here is the relevant number of ISPs for the given topology. So generally speaking, you want to consider not just a single integral with various numerators at the same time, but also what are called subtopologies or daughter integrals, where some of the propagators have been kicked out. So if we go back to, have been knocked out, so if we go back to the double box, then, for example, the kite integral is, in fact, one of the subtopologies. If we knock out this propagator, then we get a massive leg from to massless legs, and if thing, and again, we get that. So we have to consider the integral and all the daughter integrals together, and that's what this index I is really referring to. So we can write out the various denominators and their various powers. And we're going to look at a huge set of IBP identities. So if we have some L-loop calculation, then we're going to have the measures, and we're going to take the derivatives with respect to all possible loop momentum, and we're going to choose all possible choices of numerator vector V, both the external and loop momentum, and then we're going to have this object V. So we're starting with a large number of objects, and then we construct a very large number of equations. And it turns out that one of the important ideas, there are several important ideas, but one of the important ideas in being able to solve this realistically is having an ordering. So which of these integrals are considered more complicated? Which do you try to solve first? Which equations are more complicated? And that's based on the structure of the exponents and the ISPs and things like that. And Laporta, when he kind of showed that you could really build a generic technology here, gave a specific ordering. And that ordering is used, first of all, in choosing which integrals to solve, and then in what order to generate, to march through this set of IBP equations. The thing that's important to keep in mind is that the number of masters in the basis is going to be independent of this ordering. But the specific masters that show up will depend on the ordering. And in fact, that's still, I would say, a subject for investigation as to which integrals you'd actually like to show up in the basis, and there are trade-offs between different choices. So again, I'm not going to go through the algorithm in detail, but just to give you an idea, so you're going to loop over the number of denominators, and then you're going to loop of the different ways of choosing them, essentially the different subtopologies. Then you're going to loop over the excess of exponents. I mean, kind of the basic exponent is where all these alphas are 1, but you can have excess. We've already discussed the fact that doubled propagators show up. You're going to loop over all the different exponents here, and then you're finally going to march through using the ordering. So the conceptual algorithm has many, many nested loops, and to turn that into a practical code is quite a challenge. And so the one thing that I will explain is that it's possible to get rid of these double propagators from the very start, and that's it's kind of an idea which is maybe from about 15 years ago, but it hasn't yet really made its way into a very popular code. So let's look at kind of a generic IBP, and so we have a measure, and then we can imagine taking linear combinations with the derivatives with respect to different loop momentum, which I'm going to denote by the index A here. And then we have some number of denominators, and then we have a corresponding set of vectors which are associated to each of the loop momentum. So that the index A is here is explicitly summed over. And so what can we do? Suppose that we were able to find some special choice of VA so that this equation was to hold. So there's a summation here over the Lorentz index, of course, and also over the A index. So let's suppose that when you act on the derivative but then contract into this vector, you always get some, you act on the denominator, excuse me, and then contract into the vector, you always get something that is proportional to the denominator for all the different denominators. Well, if we follow through this integrand, then we can pull out an overall common factor. We, of course, get a derivative of the vector itself with respect to the set of loop momentum and then summed over A. And then we have to sum over the different denominators. So when we differentiate any of the denominators, we're going to get a -1 over the denominator. That's what the net power is then going to be 2. So, and this is going to be, of course, just the chain rule, the vector dotted into the derivative of the loop momentum acting on the. But we have just assumed we can find a special set of vectors VA. This term, of course, is the same, so that our sum now has the form of some coefficient. So this is, we can say this thing is equal to some C hat J, no sum over J. So this is going to be C hat J times dj, the denominator, and this, of course, is going to cancel. So if we're able to find these special vectors, then on line 1, we will have no doubled propagators, and we will simplify the structure of the equations a lot. And it is actually possible to do this. I'm not going to go through the structure. You have to use techniques from what's called computational algebraic geometry. And there is actually a code now called NEAT IBP due to Yang Zhang and his collaborators that implements this. It does it not in momentum space, but in the language of what are called Baikov variables, which I also don't have time to discuss. But the relevant equations that you get from putting in this constraint, I mean, you put in a basis and then you work out the explicit form of these equations. They're called syzygy equations. And you use the techniques of computational algebraic geometry, in particular something called a Grobner basis, and that's actually a good and these are both good reading topics, and would be a good topic for some course in some other school. I think there's a nice book by, I think, Little, O'Cox, and Shea, if memory serves right, which is at the undergraduate level, so it doesn't really, it's not too heavy duty in terms of the math. So these VAs are then known as IBP generating vectors, and this approach is sometimes called the syzygy approach because that's the kinds of equations that you get. And once you have these, you can use them to generate IBPs, generating in the standard way, and you still have to solve the equations, but they're simpler systems that then you start with. So IBP equations also play an important role in actually writing down equations that allow you to solve for a very large class of Feynman integrals. And we'll end up looking at that, I think, in the first half of tomorrow's lecture. But before we do that, I want to do one evaluation of a basic integral using Feynman parameters, something that you presumably learned in your QFT course, although I don't expect you will have done this particular integral. And so we will, some of you will have, but others won't. And so it'll be kind of the gateway to learning about the classes of functions that show up. So let's look at what's called the easy two-mass box. And we can choose legs 1 and 3 to be the massive legs. And again, I'll put the loop momentum over here. Let's have a show of hands. How many people know why this is called the easy two-mass box? My goodness. I was expecting at least a few hands. No, I mean, not from the, if you guys didn't know, I would be very, very disturbed. But all right, well, so here we have a K2 squared equals 0. These are the massless legs, and we have two different masses for the massive legs. So this is an integral that has 3 dimensionless ratios of scales. Of course, the other invariants are the usual ones, but now they're not just dot products. We have to include the mass terms. So let's introduce Feynman parameters, shift the loop momentum, Wick rotate, and perform the loop integration, something everyone here knows how to do. And then we get a form. Well, let me actually write out the... we get a Feynman parameter integral. So the Feynman parameters we'll call A's. And of course, they sum to 1. And then we have a certain quadratic polynomial, which I'll call x here, which is a function of the I assume everyone, how many people know how to get from that thing to this expression? No, come on, this is something you learned in your field theory course. All right, well, those of you who are a little bit hesitant can ask those who do know. And in fact, if you ask during the problem session, then I'll give some of those who do know an opportunity to do it in front of us. Anyway, this thing is again quadratic in the Feynman parameters, and I think I have a typo here, but okay. So here there's a trick, and the trick is to make the following change of variables. Which allows you to factorize this polynomial x. And because you can factorize the polynomial x, it turns out that you can actually compute this integral to all orders in epsilon using hypergeometric functions, and that's why it's called the easy integral. The other configuration of masses, you cannot do that. I mean, there is some generalized hypergeometric function, but it's not one of the classic ones. So the Jacobian here for this change of variables is just y times 1 minus y. And if we then do it, so again, the integral factorizes. So our integral is going to be equal to the same prefactor minus epsilon, and we have a separate integral over y, which has the form y minus 1 minus epsilon. So we can see right away this is a beta function. It's going to give us one denominator power of epsilon, so one singularity. And then this is multiplied by a two-dimensional integral. So there's no more delta function. This satisfies the delta function constraints. And this has the following form: 1 minus x, 1 minus z is t, minus x, 1 minus z m1 squared, and minus z 1 minus x m3 squared. And this is to the power running out of room here, minus 2 minus epsilon. So again, this integral can be evaluated exactly, but I'm not going to go through that. It's more useful to do it up to the required order in epsilon, which is epsilon to the 0. And you can do that by essentially doing an appropriate, you do one of the integrals, the x integral, for example, and then you do a partial fractioning, and in the term that has no more singularities, you can then expand in epsilon. So there'll be one term that will also have another singularity in the surviving integral, minus 1 minus epsilon, and then there'll be terms that just have minus epsilon as the exponent, so that thing is not going to produce any singularities, and there you can just expand in epsilon. So one is going to get an expression of this sort. So there's a characteristic denominator, and we have a 1 over epsilon squared. So here we've kept the exact power dependence on epsilon in the potentially singular terms and just expanded elsewhere. And I think I'm going to continue on the next board. So we have a bunch of functions that some people should recognize, but other people may not. So, and I hope everyone recognizes this function, right? So Li2, 1 minus m1 squared over s, minus Li2, 1 minus m1 squared over t. And then the same thing with m3 squared, 3 squared over s to 1 minus m3 squared over t. And then, let me close the bracket, plus something that's of order epsilon, which here you could compute, but in general, we're not going to worry about it. So how many people know what this object is in Li2? Okay, that's, so I'm not expecting everyone to have seen it before. So this thing is actually a 19th century part of the universe of 19th century special functions. So actually, if you'd had a good mathematical physics course, you would have actually seen it, but I think those are probably a vanishing breed, such courses. So let's define something that you do know, which is an Li1. So this thing is just minus log of 1 minus x, which we could also write as integral 0 to x of dt of 1 minus t. And Li2, which is called the dilog, or dilogarithm, and that name coming from the fact that it involves integrating a logarithm. And more generally, this is one of the classical polylogarithms, which Li3 and Li4 were also studied to a much more limited extent in the 19th century. So these are all functions which have a branch cut that runs from 1 out to infinity. And they all have a series expansion, which is useful for doing analytic games. And you can prove that series expansion from the definition. It's not the right way to calculate them numerically. So let's make a few observations about this integral. And I think I will not risk the chairman's wrath by going as far over as would be necessary to talk about differential equations, but we'll do that tomorrow. So let's make a few observations. First of all, the actual leading singularity here, in spite of the appearance of the 1 over epsilon squared, is actually 1 over epsilon. And that's because if I were to compute its coefficient, then I have to expand all of these powers. I get 1 plus 1 minus 1 minus 1. So generically, it is true that box integrals will have a 1 over epsilon squared, but this particular one is actually only 1 over epsilon. We have new features. We have branch points, and there are branch cuts that emerge from them. So some of them are inside the logarithms and the dialogues, but there are also some that are emerging from these terms here. There you have to, because epsilon is not an integer power, you have to choose a branch cut there, and we can see that for example, the branch point in S, you can convince yourself that's actually a physical thing. You expect there to be a change in behavior when you go from negative to positive S. On the other hand, you might be a little bit disturbed by the appearance of this denominator, because it looks as though we have a singularity in some very strange place in momentum. Incidentally, I made earlier the comment that the S34, S45 factor was the denominator of the box. If you take, for example, M3 to 0, then that's exactly what you'll get for the box that we looked at earlier. So you can see that, I mean, I didn't do the calculation in all its details. So this singularity is spurious. And you can see that by defining this to be delta and re-expressing these terms, the logarithms that emerge at order, at the finite order in, at the order 1 over epsilon in terms of that delta, and you can see that there will be a cancellation. Here, for example, in this dilogarithm, it's actually very clear, because if you can write this as delta over st, and we know that the dialog is going to start with the first power of its exponent, so we'll get a delta from there that will cancel the delta in front. And it turns out that, again, the remaining terms will combine so as to remove that singularity. And so the 1 over st minus m1 squared, m3 squared is spurious. And that is, in fact, a very general feature of loop integrals, especially when they're embedded into amplitudes. There can be a lot of spurious singularities that can be an issue in numerical evaluation. So another exercise is to show that this is true for all the remaining terms. Show the cancellation for remaining terms. And here you get a hint, which is to find relations between different dialogues, like, for example, 1 minus x and the dialogue of 1 minus x inverse. And you can do that by conjecturing there's some linear relation. And I mean, you could, of course, prove it directly, but you can also differentiate and fix the coefficients by looking at the relations between the logarithms, which are then very easy to find. So one last, or actually two last comments. So first of all, this object is something which doesn't look as though it factorizes. How many people think it does factorize? My goodness. You know it factorizes. You've even done these calculations. Okay. So it doesn't factorize in terms of invariance, but in fact, in terms of spinors, we can factorize this into an expression of this form. And that factorization is actually, can be important in showing that even the degree of spurious singularity in some expression in an amplitude is softer than what you might have thought. For example, you could get some cancellation between spinors that arise in the numerator from all the polarization vectors and this kind of expression in the denominator. So in general, we can't, of course, integrate integrals explicitly, but we can make use of the integration by parts identities to construct differential equations, and we'll look at a very simple example of one tomorrow. Otherwise, I won't exercise anyone's patience or block you from lunch, and I'll stop here.
So my understanding, when you were talking about the VAs, is that you can get the master basis of integrals just by considering the IBPs with the VAs. Is this obvious? Is it in? Shouldn't you lose some equations and so on and so forth?
I mean, so to some extent, the set of masters these days usually people take to be whatever comes out of solving the IBPs.
I see.
The more complicated question is, can you show that all of these have a different analytic structure in the same way that the triangle and the box have different analytic structures? So again, the analytic structure here being defined by the locations and residues of the leading singularities and potentially generally for subleading singularities. And there, I don't think there's a general proof of that.
I see. In particular, if you have some set of integrals, this is the kind of question that you're going to ask if you want to know if it's a proper basis.
So as a matter of practice, okay, what happens is that, so if you're worried about the analytic structure, then yeah, some unfound linear relation is unfortunate. But if you're just trying to get the computational workload down, and you have a means of computing the coefficients, even if maybe there's some hidden relation that you're not taking into account. An example of a hidden relation which people don't always take into account are these relations that are analogous to the pentagon reduction to boxes, where it's not an exact identity, but there's some order epsilon term. So if you miss a relation like that, it's generally not the end of the world in a practical calculation. And So from a practical point of view, the very fact that you're reducing from, thousands or tens of thousands of integrals to dozens, that's good enough.
Yes.
And to prove that each of these is actually analytically independent, that I think it's a hard mathematical question, and there is no complete proof in the literature. But from a practical point of view, it doesn't really matter.
Thank you.
So in the Laporta algorithm, this measure of complexity that you have to come up with, is it a heuristic thing, or is it like a hard
I
rule?
don't think there's, first of all, it's not unique. But roughly speaking, it's kind of saying that if you have more denominators, it's a more complicated integral. If you have more x sets powers, it's a more complicated integral. If you have more complicated numerator, it's a more complicated integral. There's like a list of whatever, 5, 6, or 7 different criteria that you have to march through. And it is important that this ordering kind of really distinguish all integrals so that you have a clear path to solving things. But I'm not actually 100% sure that Defire and Kira actually use that ordering. They could well modify it. I mean, Gustavo would know. Kira does. Okay, so I'm not a user of those codes because I kind of do things more the neat IBP way. But so it's well defined and it's detailed, but I don't think the details are that important. So, although I was actually going to subject you to it if I'd had more time. So, once in your life, you should probably see it.